In this video, we are going to define the wedge product, which takes a P form and a Q form and produces for you a P plus Q form. So before I give this definition, which is slightly complicated, let's take a very naive and straightforward approach and see what happens. So suppose we have a P form omega and a Q form eta on the vector space V. Now we want to take omega, some product eta. Well, let's think about this for a moment. Omega eats P vectors, eta eats Q vectors. So why not just combine them together? So tentatively we can define this product. The notation for this is a bit interesting. It's a usual product with a circle in between. This is called the tensor product. Suppose you are given vectors v1 to vp and vp plus 1 dot 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 vp plus q. Why not just define it to be just omega of the first p vectors v1 to vp. So let's just put v1 to vp here. Then just take the usual normal products, which I'm not even going to give a notation to, just like how we just write ab instead of a times b, into vp plus 1 dot 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 vp plus q. So you just take the usual product. Now roughly 2-minute check will tell you that omega tensor, so this is red, this thing is red, tensor. Okay, so this is sort of the tensor product of tensors. So omega tensor product with eta is a 10p plus q tensor if omega and eta are p tensor and a q tensor respectively. So if omega and eta are p and q tensors, then the tensor product will give you a p plus q tensor. Multilinearity is the only thing you will have to check, and it's obvious that this is multilinear. However, the alternating property is not at all clear. If omega and eta were, in addition to being tensors, they were forms, that is, they are alternating. If I interchange v1 with any other thing in v1 to vp, I will get a negative sign. Similarly, if I interchange vp plus 1 with any other thing in this vp plus 1 to vp plus q, I will get a negative sign. But God knows what will happen if I interchange vp with vp plus 1, for instance. If I do this switch, will I get a negative sign? I have no clue. There is no guarantee that that will happen. In general, it won't. In general, the values need not be related at all. Therefore, this construction does not work for forms. If you take two tensors, the tensor product will give you a tensor. However, if you take two forms, the tensor product need not be alternating. We have to somehow fix this. So the correct way to fix this is to define a way of making a p tensor into a p form. So we will define what is called the alternator that does the job for us. So this is the definition of the alternator. As the name suggests, it takes a form and takes a tensor and makes it alternating. Let T be a K tensor on V. For a permutation pi in Sk, so this is the symmetry group of K letters, on K letters, or for more concreteness, I can just write the symmetry group of 1 to dot 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 n, that is the collection of all permutations of 1 to k, sorry, not 1 to n, 1 to k. Let T be a k tensor on V. For a permutation, we can define T pi of V1 to Vk to be, by definition, T of V pi 1 comma dot 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 V pi k. Okay, so this T pi is another k tensor on V. What it does is, you first shuffle the entries according to the permutation and then evaluate T. So shuffling the entries is not really going to break multilinearity, because anyway this tensor means it's multilinear. It's a linear in each one of the slots. We are just playing around with the slots before evaluating T. So this T pi is definitely going to be multilinear if T is a k tensor. So there's no such issue there. Now we are going to make it alternating by using these T pi's. We are going to make T alternating. We define the alternator of T, alt T acting on V1 to Vk, by definition to be sine, I forgot a summation. By definition, this is just summation over pi in the symmetry group of k letters, sine of pi T pi of V1 dot 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 Vk. Okay, you just sum across all the possible permutations pi in Sk and take T pi of V1 to Vk and put a sine of pi in front. That this is indeed going to be an alternating tensor, or in other words a k form, is left as an easy check for you. Okay, so exercise, show that alt T is a k form. Okay, another exercise for you. If if T was already alternating, then tau pi equal to tau for all permutations. For all permutations pi in Sk. So once again, tau pi is sine of pi times, T pi is sine of pi times T for all permutations pi coming from Sk. Okay, so in fact you would need to use this exercise to solve this one. Okay, so I reversed the order of the exercises. First, show that if T is already in alternating, then T pi is sine pi for all permutations pi. In fact, I'll make this stronger. I will rephrase this exercise. To make it easier for you. Show that a k tensor T is alternating if and only if T pi is sine pi times T. Okay, so taking T pi should just give you back T with a sine in front. If this happens, then T is alternating, and conversely, if this happens for all permutations, so this is for all pi in Sk, if it happens for all permutations that T pi is sine pi times T, then T is in fact alternating, and use this exercise to show this one. Okay, finally, this is the one that I should have stated before. If omega is already alternating, already alternating, then alt omega is k factorial times omega. Okay, so if it's already alternating, then it's not going to drastically change. There's going to be a factor of k factorial that comes out. That's for this reason in many textbooks, when they define the alternator, they put a factor 1 by k factorial in the definition here, so that when you take the alternator of an already alternating form, you get back the form itself. But because we have chosen to keep the notation simple, we will end up with an additional factor of k factorial, but that's unavoidable. Okay. Now, we are now in a position to define the wedge product of two forms. Essentially, you are just going to take the tensor product and then make it alternating, except there will be some factors that will occur that might puzzle you, but don't worry so much about that. These constants are there just for normalizing stuff. So this is the definition of the wedge product. Wedge product of forms. Let omega be a P form and eta be a Q form on V. We define the P plus Q form omega wedge eta to be by definition 1 by P factorial Q factorial, the alternator of omega tensor eta. Okay, so omega tensor eta would be a P plus Q tensor from our discussion before. The alternator will make it into a P plus Q form. This extra factor that you see here, 1 by P factorial Q factorial, is there just to normalize stuff. Think about why you had put this precise factor of P factorial Q factorial. Think about it for a few minutes and you will understand why it makes sense to put this factor P factorial Q factorial. Okay, now I am no longer interested in general vector spaces. I am going to focus only on vector spaces on Rn from now. Sorry, only the vector space Rn from now. So henceforth V is going to be Rn. Okay, we will focus on the vector space Rn. So the first thing I want to do is study how this wedge product looks in a concrete situation. So proposition. So this is about the wedge product of the form that we have already studied in some detail, that forms dxi. Okay, so the proposition states follows. The statement of the proposition is as follows: dxi wedge dxj is just dx ij. I will explain in a moment what this means. Here I is some I1 to IP, j is the multi-index IP plus 1 to IQ. Okay, and ij is just, so these are just numbers, these are all is and jr are elements of 1 to n. Then ij is just let me just make it in fact I don't need the very general result. I can just take 1 less than ir less than or equal to n, and 1 less than js is less than or equal to n. Okay, so and ij is by definition just concatenating both lists of numbers together. It's I1 to IP, then IP plus 1 to IQ. So rather I must have written there's no j here, so I should have just written 1 less than or equal to ir less than n. There was no j index. I thought there was j also. Okay, so we are just concatenating the two lists together. So there's one more small typo. This is P plus Q, and the same thing here. This is also P plus Q. So you just concatenate the list, and the form dxi wedge dxj is dxij. Okay. Proof. Let's prove this. Proof. From our analysis of the behavior of the forms dxi and dxj, we know that if some index in I appears in J, then dxi wedge dxj as well as dxij will both be 0. Will both be 0. Okay. Now the fact that dxij will be 0 is clear. From that discussion. Think y dxi wedge dxj will be 0. Okay, so this will just be unwinding the definition of dxi wedge dxj. Once you unwind the definition, you will understand that dxi wedge dxj will be 0 if some index of I appears in J as well. Okay. Also, dxi is 0 except on ei pi 1 comma ei pi k. On all other combinations of basis vectors, this differential form dxi is going to be 0. This was part of the analysis of the forms dxi. So I urge you to go back to that example and see why this is the case. So here pi could be any permutation. Here pi is in sk. Okay. And dxi of ei pi 1 comma ei pi k is, as you will recall, sine of pi. Okay. So these are facts I want you to recall from the definition of the forms dxi and the extended analysis we did several videos ago. Okay. Now look at dxi wedge dxj applied to some p plus q tuple of basis vectors. Let's apply dxi wedge dxj to a p plus q tuple of basis vectors and see what happens. Okay, this would vanish. So this would vanish unless the p plus q tuple is a permutation of ei1 eip comma eip plus 1 comma eip plus q. Okay, you permute these entries and apply dxi wedge dxj, it will be non-zero. For any other tuple which is not obtainable as a permutation of these p plus q basis vectors, then it will be 0. Again, remember, we are assuming now that I and j are distinct. There is no index in I that appears in j, because if that happens, the previous case deals with it. Okay. Now let's evaluate dxi wedge j on ei1 comma eip comma eip plus 1 comma eip plus q. Let's evaluate it on this. This is by definition 1 by p factorial q factorial summation over pi sine of pi dxi tensor dxj of e I pi 1 comma e I pi p plus q. Okay, so here you sum over all permutations in S p plus q. Okay, now notice what happens. This is nothing but 1 by p factorial q factorial summation over pi of 1, which is equal to 1. Okay, why is this the case? Where the summation is over all permutations that fix 1 2 p and p plus 1 p plus q. So this is something that is better figured out by oneself. Let me try to guide you on the path. Here the summation was through all permutations, but if you look at each one of these terms, this is just going to be dxi of the first p things multiplied by dxj of the final q things, right? But dxi of the first p things will be non-zero if and only if the first q things is just a permutation of ei1 to eip. Similarly, for dxj of the last q things will be non-zero if and only if the last q things are permutation of eip plus 1 to eip plus q. Only in that scenario will this sum be non-zero. So you need not sum up over all permutations. You just need to sum up over permutations that fix this as a set and this as a set. Note what I mean is I fix this as a set. Okay. Now once you fix that as a set, when you apply dxi to some ei pi 1 to ei pi p, then what I get is nothing but sine of pi by the remarks before. So the sine of pi into sine of pi will just give me 1. Okay. Now I want you to figure out where I got the factorial p factorial and q factorial here also, so that it all gets cancelled off. So I want you to think about how there are exactly p factorial q factorial permutations for which this is 1, so that everything becomes 1. Okay. So essentially, let me just reveal it for you. There are exactly p factorial q factorial permutations that do this, that fix 1 to p as a set and p plus 1 to p plus q as sets. Okay. Now it should be clear to you that this gives 1 once you understand why there are exactly p factorial q factorial permutations. So what has happened is dxi wedge dxj we already know is an alternating form, and we already know that it is non-zero only on this basis vector and permutations thereof, but how it behaves on those permutations is going to be precisely determined by the alternating nature. On this is 1, but this form dxij also has the exact same feature by definition. On that vector ei1 to eip plus q, it's going to be 1, and on permutations of those, on all other vectors it's going to be 0. Therefore net conclusion, dxi wedge dxj equal to dxij. Okay. Let's see a simple corollary of the fact that dxij is dxi wedge dxj, this is just expressing dxi in terms of the basis forms. If I is I1 to Ik, then dxi is nothing but dxi1 wedge dxi2 wedge dxik. So I want this corollary is rather trivial, so I want you to prove it yourself. Now let's move on and study some properties of the wedge product. Properties of the wedge product. Let's list out some basic properties. First is bilinearity. What this says is, if you take omega plus phi wedge eta, where omega, phi and eta are some forms, this is just omega wedge eta plus phi wedge eta. Okay. 2. This is called skew symmetry. This says omega wedge eta is minus 1 power pq eta wedge omega. Okay, where omega is a p form and eta is a q form. And finally, we have associativity, which merely says that omega wedge phi wedge eta is omega wedge phi wedge eta. Okay, so all of these properties are straightforward to prove. Let's go about our job and prove them one by one. So you have omega plus phi wedge eta. This is just by definition alternator of omega plus phi tensored with eta, right? And it's immediate to see that for tensor product, bilinearity is rather obvious because it's defined in terms of a usual product. This is nothing but alternator of omega tensor eta plus alternator of omega tensor eta. Okay, and this proves that this is omega wedge eta plus phi wedge eta. So the key step is just observing that alternator of omega plus phi tensor eta is just alternator of omega tensor eta plus alternator of omega tensor, oh sorry, I made a typo here. This is phi tensor eta. So just checking this one step, I'm going to leave it to you. It's straightforward. Okay, so the second step, I will in fact prove associativity. For associativity, we are going to now use the fact that I am restricting myself to the vector space Rn, and I'm going to make use of these special bases. I'm going to write omega as summation I dxi, ai dxi, eta as summation j bj dxj, and phi as summation over k ck dxk. Okay, now expand omega wedge eta wedge phi by bilinearity, and observe that both sides will turn out to be this ginormous triple sum. Both sides is summation over I j k ai bj ck dx ijk. So essentially you're going to write down omega as this, eta as this, phi as this, then take the wedge product of this by bilinearity and expand. You will get a ginormous collection of terms. Then take this wedge product, you will get an even more ginormous collection of terms. Just think for a few minutes and you will understand that you will get this. The other side is similar. The other side will also give you this. So both are same. Okay. So of course, I have not mentioned what dxijk is. It's has the obvious meaning. I'm not going to say anything more. Okay. Skew symmetry. Let's expand one term of omega wedge eta. One term is going to look like some ai bj dxi wedge dxj. Of course, omega wedge eta will be a bunch of terms that look like this. I'm just focusing on one term, and this is by our earlier result ai bj dxij. Excellent. And by the fact that you can expand dxij using the basis, the one forms, basis of one forms, this is just ai bj dxi1 wedge dot 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 dxip wedge dxj1 wedge dot 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 dxjq. Okay. Now I want to interchange the positions of the various terms. So I want dxj1 to be the very first, this dxj2 to be the second, and so forth. So what I do is I move this dxj1 all the way to the first term. Okay. To do that, I need to repeatedly do a transposition with the entry that is preceding it. So what I do is I first interchange dxj1 with dxip. That will give me a negative sign. Then I interchange dxij with this next entry. And I keep doing this p times and I will get to the beginning, right? So essentially what I'm saying is using a product of p transpositions, we can move dxj1 to the front. Okay, this will introduce a negative sign. This will introduce a negative sign. Okay, now we have to now move dxj2 all the way. Oh, this will not introduce a negative sign. I made a slight mistake. This will introduce the sign minus 1 par p, proof. Okay, this will introduce the sign minus 1 par p. I am asking you to prove why this is so. Okay, now move dxj2 to the front. This will introduce another sign of minus 1 par p. Okay, net upshot is aij dxi wedge dxj is this is ai bj dxi wedge dxj is ai bj minus 1 par pq, because you'll have to do this q times to move all the dxj1 dxj2 dxjq to the front. Each one of them is going to contribute a minus 1 par p. You will get dxj wedge dxi. Okay, so this concludes the proof of the skew symmetry. Because we have done it for these basis forms, you just use bilinearity and expand the whole thing out and do this interchange at each stage. You will get minus 1 par pq everywhere. Okay, so this proves the basic properties of the wedge product. I'm going to end this with an exercise. Let T from Rn to Rm be a linear map, and let omega and eta be forms on Rm. Show that the pullback of the wedge product of omega and eta, is just the pullback of omega, wedge pullback of eta. Okay, so this will test your understanding of both pullbacks as well as the wedge product. This is a course on real analysis, and you've just watched the video on the wedge product of form.